for inviting me to. I was supposed to remind you about the recording, but I see you did it already. And thank you very much for inviting me to present the great ARMA community. With your permission, actually, I turn off my camera to save some bandwidth. Good morning, everyone. I appreciate your time listening to my presentation today. As the title says, I'm going to talk about the technology that we basically recently developed and enables us to basically predict and prevent fractive screen out in real time. I'm giving this presentation on behalf of a wonderful team that worked closely together to develop this technology at Petrolern. So I would like to thank Dr. Farouqi, Hasbel Yadi, Manju Marugesu, and Dr. Hao Kang for their contribution to this project. So here is the presentation outline. I will start by this.
Could you please share your screen?
Oh, it's not sharing now? Oh, sorry about that. I don't know what happened. Let me try again.
John, I wonder if he has to have his camera on to share the screen.
Not really, it shouldn't be the problem. So let me just try it one more time. I don't know why it stopped in the middle. Okay, do we have it now?
Yes.
You do see? Okay.
Yes.
Yes.
Yeah.
Okay. Okay, sorry about that. So here is the presentation outline. I will start by describing a screen out problem and its consequences. Then I will introduce Petrolern's solution to this challenge, which is a machine learning based solution that predicts screen out events before their occurrence and alert the field personnel so they get enough time to take prevention actions. Sorry. So screen out is one of the major operational challenges during hydraulic fracturing operations. The most common type of screen out is tip screen out, TSO, where induced fracture gets packed off by proppant with no further propagation. And thus, the pressure builds up. Such pressure spike poses several risks in the field. Right, it may exceed the production casing burst pressure or surface equipment pressure limitations and jeopardize personal safety. There are also huge negative financial and economic impacts associated with tip screen out, which some of them include, losing the stage and, of course, the expected production from the stage. Cost of flowing the well back through flow back equipment, cost of post-screen out injection test, of course, delay in turn-in line per day, which will lead to lower net present value, cost of coil tubing or snubbing, should it be required, and several other post-screen out costs and delays. Overall, tip screen out has been recognized as a severe obstacle against safe, efficient, and cost-effective hydraulic fracturing treatment. So I think the value of having a technology to forecast screen out ahead of time and enable prevention of the screen out is quite clear. So with respect to the risk of hazards, it can prevent bursting the production casing and surface equipment and potentially save personnel's lives, which is the most important value to me. With respect to the cost saving, just for your information, cost of flowback is roughly 10 to 40,000 US dollar per stage. Cost of cleanup after screen out is 80 to 150K, and so on. Note that the main economic impact is losing the opportunity to have long-term production from the lost stage. So value is to keep operations safe, on budget, and on schedule. The available pre-diagnostic screen out methods listed here definitely help optimize the frac design to kind of minimize the screen out risk. But honestly, they never guarantee that the screen out won't happen. And none of these methodologies provide an automated predictive capability in real time. So in fact, the current real-time approaches are very subjective and depending on the skill and experience of a company representative who is sitting by the screen, monitoring the pressure curves. And
Ahmed, this is John. I'm sorry to interrupt, but I'm getting a lot on the chat that your mic is really giving giving us.
Really? Okay, let me try a new microphone. Hope it helps a little bit.
Ahmed, your voice was very clear when we were talking early on.
Okay, I don't know what happened, so let me try another microphone here.
Hello, John. Is it any better?
Yeah, if you just turn up the volume, it's quite clear.
Okay, let me work on the volume now. I'm sorry about that. So how about now?
I think that's good. Yeah, I mean, the more volume, the better.
Okay, is actually the maximum, but I try to close to keep my mouse close to the microphone as much as I can. Okay. Let me go back to, so you're still seeing the slides, right? Just to double check.
Indeed.
Okay, so I was talking about the current real-time capabilities that industry has with respect to identifying the risk of a screen out. Is basically a company representative or company man sitting by on site, looking at the screen, looking at the curves, and based on its experience and knowledge, decide basically if there is any risk of a screen out or not. So it's very subjective, right? There's nothing, there's no consistency between several people doing the same thing, right? But the fact is that availability of now high resolution data from fracturing processes in real time promotes to rely on AI-driven models and leave the decision making for data itself rather than personnel with no consistency. So our hypothesis here is that a screen out can be diagnosed ahead of time with the help of no advanced machine learning. Here is what we are trying to do. This is a bottom hole pressure versus time curve that we typically monitor while fracking. What we want to do is to forecast this pressure in the future time and then decide if this pressure is associated with risk of a screen out or not. Thus, we developed two modules. Number one, a time series predictor to forecast pressure in future. Our goal is to basically forecast at 1 to 2 minutes in future. And then number two, an event classifier to classify the predicted pressure to either a screen out risk or possibility to continue pumping, right? To improve the results accuracy, we also developed a third module called decision maker. Its role is basically a reinforcement learning algorithm, and its responsibility is to learn from the first two modules and make the model smart enough to basically learn the dynamic changes that were not captured during the training itself. So the first step is, of course, data collection and processing. We first started with new data, basically the raw data collections from 3 major shale basins in the US. If I'm not mistaken, there are Marcellus, Eagle Ford, and Permian. Then we did data cleaning and conditioning like any other ML-based approaches to be ready for feature ranking. For the feature selection and ranking, we considered almost all the important data acquired during hydraulic fracturing and ranked their importance using random forest algorithm. Please accept my apology for not showing the features due to confidentiality here. I really hate this, but it is a requirement for SBIR funded project. That is the case here. But I promise this is the only part of the work that I have to keep confidential. So after understanding the importance of the features, for the time series predictor module, we collected data from several independent stages from the 3 basins. So the train model will be generalized. The example here shows one of the stages. We picked 5,000 seconds of bottom hole treating pressure data, 70% of the data used for training and 70% for testing, which is a typical approach in machine learning. And we conducted the training for several input and output lookup windows because it's a very important parameter here, the lookup windows that you see here. So we have to actually test different sizes and optimize them for the best results. These windows will then be shifted to the right to form mini sequences, creating the rows of the data for a supervised learning. For the classification module, we made sure that the features selected were well distributed. We had extensive expert opinion to classify each set of data, the actual field data, as either continue or screen out for training purpose. It's very important to have equal number of continue or screen out examples to avoid training bias, as you can see here. It's almost 50-50 in our case. So let's talk a little bit about the models and methodology that we followed. Our time series prediction model is an adoption of the recurrent neural network. So as you know, RNN uses sequence of data to predict a single or sequence of data in future. The hidden layers in RNN store information from past layer and then transfer them to the next layer. But the problem with RNN is that during back propagation from the loss function, we may lose gradient or have vanishing, gradient problems, as you see here, especially if the input sequence is long, right? So in our case, excuse me, we modified the RNN to become like long short-term memory, LSTM. And LSTM has gates of memory where necessary information is stored and unnecessary information is forgotten. So we kind of tackled this shortcoming by RNN using LSTM concept. So as I said, LSTM has gates that decides which values to keep and which ones to forget. The input gate determines how much of the current time network input is reserved into the cell state, preventing insignificant content from entering the memory cells. The forgotten gate determines which cell state information is discarded from the model. So LSTM has the option to add or delete information from the cell state that controls how information is basically propagated through the layers. Gate in LSTM cell controls how much of the current cell state is discarded. So after all, we developed a customized RNN augmented by LSTM and gated recurrent units for our prediction module. So as for the classification module, we tested several models that are listed here. Of course, I'm not going to go through all of them, but the tree-based models, including random forests, came up to be the most accurate ones. A decision tree is used to discover features and extract patterns in large data sets, and they're really good in it. But a single tree can actually result in wrong classification. So considering multiple possible classification through a forest of trees and taking majority voting typically result in a very high accuracy. And this is exactly what we did here. So in our case, we decided to go forward with the random forest. And now walking you through the result a little bit. Here I'm showing some of the prediction results using different window sizes and different epochs. As you see, we have tested, windows of 30, 60, 100 seconds, epochs of 20, 50, 100. Generally, the accuracy is very high, but the highest accuracy comes from the 30-second window size and epochs of 50, the green section here. And remember, the resolution of the data was every second here. So we evaluated the LSTM model based on a base case that predicts bottom hole treating pressure for the next 1 second. Of course, it's not a great achievement, and it's just for evaluation purpose, right? We really want to go far deeper into future to do the prediction. But for evaluation purpose, it was a good actually approach to go start with the 1 second. We conducted grid search to determine the best number of epochs and lookup window sizes. We did a lot of basically back and forth evaluations, trying to optimize this. And as I said, best accuracy was for an input windows of 30 seconds and epochs of 50. Here, we applied the prediction for next time step for various blind test cases. The accuracy for all models came up to be more than 99%, as you can see on the basically plots. So here, the real values, the actual data are shown in green, and the prediction values are in orange color. And there is a confidence interval that basically shows the uncertainty around the model.
Ahmed, could you please come closer to the mic?
Oh, yeah. Sorry, I forgot about that.
Oh, thank you. That's right.
Thanks for letting me know. So for the next 30 seconds, which was a much challenging basically task, we took advantage of a similar LSTM architecture to predict the bottom hole treating pressure. The 30-second prediction is not as good as 1 second, as you can see on the plots, but it's still good enough to make a screen out prediction. It's almost, I mean, all of them are actually over 95, 92%, around average 94%. The reason why basically this accuracy is less than the 1 second goes back to the lower accuracy, basically using only the previous pressure values to do the prediction, meaning that dynamics of the data is missing here, right? The accuracy will be improved if we use larger training data sets in longer time scales, basically time frames. On the right, you can see the result of the same, exactly the same blind set test cases with the 1 second basic prediction. So talking about the classification module, the table here shows the comparison between all the classification modules tested, now including random forest, extreme gradient boosting, extra trees, gradient boosting, adaptive, gradient boosting, artificial neural network, support vector machine, and logistic regression. So the numbers are here, and as you can notice, and I mentioned before, random forest had the best result. The confusion metrics for random forest shows the highest true positive and true negative values, as you can see here. So we decided actually to use this machine learning approach model to include in our basically modeling. So here I want to elaborate a little bit on the results. We combine the optimized time series, the predictive model, with the classification model. So the result shown here is an example of a fracking stage where the next second and the next 30 seconds are predicted. As you see, so this is basically the 1 second prediction and the 30-second prediction. And both predictions here show that we can continue fracking because there is no sign of, screen out risk coming up. We can basically note that as we want to predict longer times into the future, the accuracy of the model typically decreases. And to be honest with you, going from 1 second to 5-second prediction to 10-second prediction, 30 seconds, 1 minute, the effort and challenge gets exponentially, higher and higher. So I mean, it takes a week to develop predictive code basically for 30 seconds, or let's say like 10-second prediction. You want to go from 10-second to 30-second, it takes 1 month, and so on. So it's really getting more and more challenging to predict, further in time. Currently, what we are doing at Petrolern, we are enhancing the model accuracy by adding more dynamic parameters and including the decision maker module that I mentioned before, the reinforcement learning module. And as of today, we have been successful actually to increase the prediction to close to 1 minute. I think 1 minute is roughly good enough for people in the field to stop, injecting proppant, which is the quickest and the most basically reliable way right now to stop or prevent a screen out, right? Because a screen out is, as I mentioned, is the packing off the proppant in the fracture tip. So the sooner we stop injecting proppant, the less costly to basically clean up the stage, even if the screen out happened. But our goal here is to reach 2 minutes prediction in time, and with that providing enough really time for field personnel to safely prevent a screen out. Just the status of our current status of the projects. We are doing this further development, but we are communicating with several operators in different basically shale basins to kind of test the technology, to pilot test it and see, how reliable is the model. And I know with the data that we used so far from the 3 basins, it seems very promising, and it seems that it is able to predict the screen out. But we really want to get into the field and do some real-time testing and see how the technology is working. So we are open, actually, if you know operators that are interested to test this technology, we are open to discuss and basically apply this technology at no cost. So with that said, I think I'm done with the presentation, and I'm open to answer questions from audiences.
Hey, thank you very much, Ahmed. We do have some questions. Let's see. Can you see the chat, or do you want me to
Let me
describe them?
I didn't check it, but I can go to the chat, and you are most welcome to read it to me if you don't mind.
So Ed Sieberts has had a couple of observations and questions, and Ed's first question was, how many pressure records did you collect? Random forest prefers a large number of samples.
Yeah, let me go back to the slide with these numbers, actually. Yeah, we were actually looking at 200,000 rows of data, right? From different stages, independent stages, and from 3 different basins. So that's the volume of the data that we use to develop basically technology up to 30 seconds. But after that, we actually got access to more data from different basins to add more basically dynamics to the model. I don't have actually that number in mind right now, but this is roughly what we use to develop the technology.
And then Maricela Sanchez-Nagel wants to know, is the methodology valuable or possible with surface pressure?
I'm not sure if I get the question. Is the methodology valuable, possible with surface pressure? Yeah, actually we use surface pressure. It doesn't require the downhole pressure. Of course, if we have downhole pressure, it becomes, I mean, it significantly increased the reliability of the technique, I believe. But all the data we received was basically surface data, and the bottom hole pressure was calculated.
Okay, cool. And Ed Sieberts has another observation, and Ed candidly admits as he's struggling a little bit to understand how good the predictions are, even for the 100-second window. And how does the model know that the pressure will go up rather than down 100 seconds up? He's trying to understand what parameters drive the model.
Yeah, I think I should have actually put a very basic slide that. Oh, let's talk about here. Let's see. Now, unfortunately, I don't have that simple slide that explains. But you know, the history of the downhole treating pressure kind of shows what's going to happen next, right? There are a lot of hidden patterns, right, in this downhole pressure data that only machine learning can capture exactly what these patterns mean, you know, in future, right? So there are specific patterns that shows that pressure will keep going up and end up with a screen out. There are certain patterns that shows that, you know, it might get flat, right? It means that geometry of the fracture is propagating in a certain geometry. I don't remember exactly if it is related to more height growth or basically extension, lateral extension. And also there are patterns that show that the pressure will drop, which is associated with basically different geometry of the fracture, right? It's exactly what we are trying to do here using machine learning to improve basically capability and compare with the people sitting and looking at these curves to be able to actually predict what's going to happen in the curve next. I don't know if I could answer the question clearly here.
Okay.
But here I have actually Manju with us, who is basically heavily involved in machine learning part. And if there's any extra explanation needed, Manju, you can help here. If John doesn't mind.
No, by all means.
Yeah.
Yeah,
I don't see myself as a data scientist, so.
Yeah, I think you've covered that question really well, and kind of going off of that as well, the model, basically what a model learns is trying to predict what comes next based on what it sees before. It's not like a model is not 100% physics based. So if you look at it that way, that's why the accuracy of the model that we show here was about 30 seconds. And Dr. Soroush mentioned that in the end, we are also considering a lot of dynamic parameters to predict longer time in future. So if you look at just this figure based on pressure alone, our accuracy is about 30 seconds because that's what the model sees. That's the lookup window that the model sees in order to predict the future value.
Thank you, Manju.
Okay, thank you. And Dan Moose, Dan had a question as to what is the upper limit of the time you think you can predict if the model were perfect and why?
Yeah, that's a good question. And hello to Dan, long time no see. As I said, I mean, we think, no, as we increase the prediction time, accuracy will definitely, drop. According to our evaluation, reaching 2 minutes prediction provides enough time for field people plus the accuracy will stay still in a very reliable, range. More than 2 minutes, as I said, is very challenging to achieve something that is still reliable. But the more the prediction time is of course better for personnel in the field, right? But our assumption is that 2 minutes is basically the optimum prediction time.
Okay, and Ed has another question, and it's probably the tough one in terms of how much physics is actually involved in here and what sort of assumptions are made. What sort of assumptions are made? I mean, are you assuming uniform rock properties along the fracture growth path? Are assumptions made about the treatment, et cetera, et cetera?
Yeah, this is a very good question, and the answer is there's no assumption. We are purely working based on field data, right? And leave everything for the machine learning to basically capture patterns and decide. So I mean, it's regardless of the rock being heterogeneous or anisotropic, is based on large volume of data, and this is the value of the machine learning. So it is not a physics-based machine learning. Okay, thanks. I think you've answered Dan's second question that appears, and then Yufeng Li is interested in what data are used as input when using LSTM neural network to predict the pressure. Yeah, that's the part that I didn't show actually.
Okay.
Yeah, if you, I mean, don't get disappointed at me, let me not answering this question actually. Yeah, I mean, we looked at all the frag parameters, all the parameters that basically we acquired during fracturing, but the features that were important, I mean, I couldn't actually show because of confidentiality. Sorry about that.
That's fair enough. And James Rogerson has a question or an observation, and James is suggesting it would be very interesting to understand the feature selection used for the model, and that's maybe along the same lines. Are you using a neural network to select dominant features to predict screen out?
Yeah, I don't mention the features, but we use the random forest, as I explained. We didn't use neural network for feature selection and ranking. It was random forest, and random forest is typically the best algorithm for feature selection. I think the whole community agree with me on that.
Okay, and then Madi has an important question. How fast is the model able to predict 30-second or 1 minute
It is real time. It is real time. Right?
It is real time. Okay. Okay. And I think those are the questions I see. Does anybody else have questions? I mean, and we're actually open to be a little more freewheeling here if somebody wants to just speak up.
Sorry, John, I actually cut some of my slides to make sure I stay in time, but I think it was too many.
Well, that's okay. I think people
more time for questions.
People understand what you've done and appreciate definitely appreciate the value of this.
John, this is Ali Danishi. Can I ask a question?
Just one, Ali.
Yeah, given the very variable nature of a fracturing treatment with rates changing, sand concentration changing, fluid viscosity changing, how reliable is the predicting what's going to happen when you consider the large number of variables?
Yeah, thanks, Ali. That's a good question. And some of the parameters that you mentioned.
Can you speak louder? I can hardly hear you.
Can you hear me now?
Yes, thank you.
Okay, good. Thank you very much for the question. So all the parameters that you mentioned are actually included in the data that we developed the technology based on. Now we are talking about 200,000 rows of data. So we believe that we captures actually most of the features, important features, but your questions kind of back to that dynamic data that we are addressing with adding that decision maker module to our technology. So that will basically, it means that I mean, the tool will learn from any previous predictions, right? And keep improving the reliability of the predictions. So yeah, there are different, parameters, variables involved here, but the large volume of data kind of address all those, parameters. I cannot say that is, I mean, I'm 100% sure confident about the performance of the model, but so far, all the data that we have used, we are over 92% accuracy.
Okay, thanks. Do we have,
John, is there time for one more question yet?
yeah, just like Ollie said, just one question from you guys.
Hamid, thank you much for your presentation.
My pleasure.
Just a little bit outside of what you talked about, but I suspect you've thought a lot about this, but how do you vision screen out occurring for the unconventional shales where we know we have this complicated three-dimensional fracture network? How do you envision that screen out is actually occurring in those versus a conventional sand or carbonate where you may have one planar fracture?
Yeah, again, it goes back all to, I mean, to monitoring the subsurface and surface, pressures and parameters. If your question goes back to why, I mean, we see this type of problems. I mean, TIPA screen out typically happens because of the complex geometry of the fracture, the near wellbore condition, tortuosity of around the wellbore. And these parameters typically increase the chance of TIPA screen out. So with modeling, with optimization, we can kind of minimize this possibility of frac screen out. Now, I mean, these days, if you talk to some companies, they claim that we don't really have screen out problems anymore. It partially might be just claim, but might be actually because of doing proper geomechanical modeling and frac basically design to optimize the frac for no screen out, to minimize the screen out. But our approach is mainly passive. So we assume that a screen out might happen. So we use all those features, parameters that are important, are effective on screen out, and try to do prediction by use of power of machine learning here. Is one of, I mean, I honestly, I'm not a big fan of machine learning myself. But this is one of the examples, because machine learning can be very wrong, very misleading, right? I think all people out there, they know that. But this is one of the best examples to me that machine learning can add value, right?
Thank you.
We do have one more question from Lijiang Wang, and the question is that. And you maybe have already answered this, that there are 200,000 rows of data. That's about 50 stages, 4,000 seconds for one stage, let's say. Just wondering, in terms of some of the metrics of what's in what you've evaluated, how many stages, how many basins, and maybe you can just recap what you did there.
Yeah, exactly. It is what we are doing right now, as I mentioned at the end. Going from 30 seconds to 1 minute, you need more data. From 1 minute to 2 minutes, you need more data. And the larger the data sets, the longer the time frame, the more reliable the results. And exactly what we are doing. And again, if you are working for shale gas developers, companies with unconventional capabilities, we are really open to include your data in our basically code technology and improve our reliability and hopefully help you with some of your screen out issues.
Okay, and Hossein Davari has a question on accuracy. How is the accuracy of the time series prediction calculated? For example, if the observed pressure is 10,000 psi, does that mean 100 psi error in prediction is 99% accurate?
Okay, let me get Manju here to help me, because Manju.
Yeah, we looked at accuracy and the root mean square error, and it is based on, we compare the predicted pressure with the observed pressure, and we find the accuracy based on the observed pressure. Yeah.
Yeah, thank you, Manju.
Okay, anyone else? Well, hey, this is very provocative. It's an important of things to come, I think, in the business, and it's really nicely done where there's a combination of machine learning and some physical insight and experience. And I'd really like to thank you, Dr. Soroush, for just a fantastic presentation.
John, can I add just one comment here? Because predictive coding is actually very popular in other disciplines, like electrical engineering, to predict a different type of risk, right? It can be applied in different applications in oil and gas industry. For example, we are applying kind of the same methodology to predict kicks and loss circulation during drilling, which are really costly, problems and create a lot of cost and non-productive time during drilling. So it's not just the only application for it. There are many other applications that maybe other people can use this type of predictive coding to avoid those risks. I just wanted to mention that there are other applications that we're working on as well.
Indeed, indeed, and I agree with Ed's final comment that this was a very interesting presentation, and I really want to thank you. As I said, I think it's a sign of things to come, and so good luck with your advances in this.
Thank you very much, John, and appreciate the time given us to give this presentation. And I would like to thank all the audiences for bearing with me and listening to my presentation. Thank you very much, all.
Thanks sincerely. Okay. Thanks, everyone.